Welcome, everyone. So let me introduce Jamie, who's a professor, I believe, at Heriot-Watt University in Scotland. So Jamie is known for many contributions to computer science, including the invention of nominal techniques and nominal sets, for which he received the Church Award along with Andrew Pitts. And some of you might remember that he gave a talk at Galois a few months ago about UTXO blockchains. And so after this talk, we started a conversation on another blockchain topic with Jamie regarding a blockchain called Stellar, for which we've done some assurance work at Galois. And Jamie found it interesting and very quickly came up with a new way to understand the fundamentals behind the Stellar blockchain, which is what he's going to talk about today, I believe. So with this, Jamie, the floor is yours.
Juliana, thank you very much. Thank you to Richard and Galois for the invitation to speak. And Juliana, thank you for the many fascinating conversations, which for you were very early in the morning and for me were rather late. So I appreciate your sacrifices. So let's talk about, if you can't see the slides, please speak up now. Cool. And just so you know, I am here for you. So if you have any questions at all, just butt in and interrupt. I don't care if I don't come to the end of the slides. That doesn't matter. What matters is that you understand what I'm speaking about. I very much welcome interruptions. If you understand that, please interrupt me now. Put up your hands or something. Is there a put up your hand button? So if you could put your hand up just to reassure me. Do we have a?
There is no useful button like that.
Oh no, no, there is, there's a raise hand. And there are reactions, yes. So if you go to the bottom right, there's a little 3 dots with more on it. Click on that, you can clap, you can give me a thumbs up. Everyone give me a reaction, please. $30 people out there, come on, I want to see some thumbs. I can see the video feeds and lots of puzzled people.
That
well,
might
I'll
not
leave
be
you
a thing in this version of the client. I don't know.
Ah, the raise hand button was in the participants window. Interesting. Okay, well, on my try to find a raise hand or react button, because I am going to ask you to react so I can carry on. That is your task while I speak. I will move on, but I need feedback. So. Let's talk about consensus, ladies and gentlemen. You know what, dimwit, that's fine, so long as you can react, even if you're just chatting in the window, just something so I can get a measure of reaction. Because, I mean, to state the obvious, I'm sitting here in a box in Glasgow. I've got no idea what's going on unless you react. So our only interaction is that which you choose to electronically send me. Raise hand is good, that's fine. So let's think about consensus. In the real world, we base decisions on sets of agents that we've decided that we trust, right? That we're going to cooperate with. So for example, consider the set of my wife and my mother-in-law, or The Economist, BBC, and the New York Times. That places me, doesn't it? Weather Outlook, BBC. We can call these systems quorums. And if you think about it, these systems have some interesting properties. They are open. That is, people and institutions appear and disappear. Newspapers are founded and fold. I make friends with people. I go out of friends with other people. They're also unpermissioned. So there's no global rule that says, do as your father and mother say. There may be recommendations, but it's not imposed. You don't have to, right? So when I wrote that, I thought, yes, but it is a commandment, but it's also a point of the commandments that you don't have to follow them, right? So it's not forced. They're also not percentage-based. It is not the case that if you observe more than half of the people around you drinking beer, that you will feel obliged to drink beer. It's also local, these quorums. So my wife and mother-in-law are different from yours. And finally, they're mutable. And I was thinking of good examples of this. I thought of Henry VIII. Oh, here's quite an interesting case. He changed his marital quorum 5 times. And on one occasion, when the Pope told him that he couldn't get another divorce, enough Henry already. So Henry VIII actually changed the entire religious quorum structure of England from Catholic to Church of England. He actually invented a quorum which could then agree that he could have a divorce. So, you know, I think that's pretty good. So what is, I ask you, an open permissionless voting system with local mutable quorums, which is a bit of a mouthful, but that's the real world. That's how the world actually works. And when does such a system mathematically, what mathematical restrictions could we put on the system to ensure that it remains organized and coherent? Because, let's see if I haven't figured out how to point. Can I point? Aha, spotlight. So yeah, here, can you see this little dot moving around?
I cannot.
I cannot either.
You can't?
Yeah, there it is.
No,
it appeared now.
There it is. Okay, I'm drawing a letter H. Hello. Okay, that's good. So this does not intuitively invite the idea of structure, right? There's very little control here. So you'd expect a system like this to degenerate into chaos, wouldn't you? It will be anarchy. People just do whatever they want. But in fact, in the real world, that's not what we observe. So now I need to change slide. What actually happens in the real world is that systems like this self-organize into surprisingly stable pockets. Who we go to lunch with, I don't know about you, but generally speaking, there's a fairly constant sort of quorum of people that I go to lunch with, or used to before the virus, who we vote for, what news we believe, what brands we wear. And it's, if you think about Stella, which I would argue is an implemented manifestation of one of these systems, Stella also, it's a consensus protocol, and it does appear to work, more or less. To the extent that anything in this field can be said to work, Stella works. So why? What is the mathematical essence of this thing that explains its stability? So I, in this talk, will outline such a mathematics, and it's based on conversation with Giuliano, mostly of this paper referenced here. So how am I going to do this? Well, let me explain. I'm a mathematician, so I'm going to reach for a tool which I am familiar with, which is topology. So here's a picture of a topological space. Could you please raise your hands or clap or whatever if you have seen a picture like this? This is a picture of R squared. Is this familiar? React now, please. You would if you could, right? Tristan is looking puzzled. Everyone else has, right, okay, so I need some kind of reaction. So using the zoom function, please tell me if you do not recognize this picture and are not familiar with R squared. You guys are a tough crowd. Oh, did somebody react? I can't tell, it flashed. Ah, okay. Mike, thank you for that. Oops, hang on, I need to get back in. So Mike, you haven't seen a topology, so, okay, thank you for the comments. So ask, perfect, thank you. So I'm going to, correct me, have you seen the real line? You know, like real numbers, you're familiar with that, correct? So if you're not familiar with the real numbers, speak now. If you are familiar with the real numbers, say something now, please. Cool, thank you. So the real numbers are a topology. They have a notion of open Oh, okay, Martin, thank you. So the real numbers are just like decimal numbers, like 3.1415926, that kind of thing. And they're organized into a line, which is called the real line. And if you put two copies of the real line orthogonally to each other, then you get R squared, which is basically two parameters. So an example of an element of R squared would be 1, 1, or you know what, it's like map coordinates. Okay, so interrupt me if you have any questions on that. This is a universe of map coordinates. So here's a point. Let's say that this is, I don't know, let's say that this is New York, why not? And this is a neighborhood of New York. So I literally mean, in a geographic sense, some region around New York. And this is a larger region of New York. And I'm going to call this an open set. And it's open because it doesn't have a boundary. Every point in it is surrounded by its own little region. So you could think of this as the observable universe, in fact, just as an example, because every point in the observable universe is surrounded by another little, by a smaller observable open set, right? We live in R3. We live in a three-dimensional world. So to address a point in the observable universe, you need three coordinates. I'm not considering time. This is a closed neighborhood because it has a boundary. The points on this solid line here, they don't have a neighborhood that is entirely within this closed neighborhood because they're on the edge. That's the essence of a boundary. If you take one step in the wrong direction, no matter how small, you're over the border. Whereas here, we can approach this boundary, but the boundary itself is not part of the open set. Smile if, well, you can't do that. Please react if you have any question to this, please. Okay, please react if you have no questions whatsoever, and this is completely clear. Come on, guys, help me out here. Thank you. Okay, now, if you still, you haven't seen this before, then the main point is that this is a completely standard mathematical definition. If you didn't study maths in uni, you might have missed it, but this is off the shelf. And here is the mathematical definition. So I'll just read through this. A topological space is a set of points. Here, there's your set of points. So if you think in terms of maps, then the set of points is every single possible point there is in the world, in the universe, whatever. And then we have a set of open sets, which are, an open set is a collection of points, and the collection of open sets has to be closed under two operations. Arbitrary union, so any collection of open sets, if you take its union, is another open set, and any finite intersection of open sets is still an open set. It's not obvious that this should be the right mathematical abstraction of this thing here, but it is, and that's just an off-the-shelf fact. And the difference between an open and a closed set is that an open set contains an open neighborhood of every point within it. So there's no boundary. Wherever you are in this open set, if you take a small enough step, you'll stay within the open set, whereas a closed set may have a boundary. Please react if you're okay with what I've said so far. Thank you. And please react if you have a question. If you have a question, please ask now. Okay, I will carry on then. This is new. This is a semi-topological space. A semi-topological space is still a set of points and still a collection of open sets. So these are kind of neighborhoods or regions. They're still closed under arbitrary unions. All we lose is we lose closure under finite intersections. That's all. By analogy, so this looks like a topology, but you just lose one mathematical property. This is quite common. that is, I haven't seen this definition written out, but it's quite common to take a structure like a group, and then you delete an axiom from groups and you get semigroups. Or if you take lattices, delete an axiom from lattices and you have semi-lattices, and so on. Yes, so that's fine. I will carry on. Please stop me anytime you need to. And now I will attach a intuition to this definition. So a neighborhood, an open neighborhood of a point P is intuitively a collection that P is in. And if P looks around and sees some open neighborhood of itself that is all doing something, then P will do that thing too. It will cause P to act, right? Now, the reason that semi-topologies lack the intersection property is because of this example here. Here are two of my quorums, me and my wife, and me and my mother-in-law. Now, either of these sets is sufficient to organize an action, such as a lunch out. But the intersection of these two sets is just me, and that is not sufficient to organize a lunch out. So that's why semi-topologies lack the intersection. Agents' points could be members of several different quorums, and it is not necessarily the case that the intersection of two quorums, the intersection of two semi-topological open sets, is an open set. Any questions? Okay, please type something in the chat if you're happy with this and I can carry on. Diachki, thank you very much. More reactions, please. Good, thank you. Okay, I will carry on. That's nice. I'm liking these reactions. That's very helpful. Thank you. Keep it up. Really, it's important. Okay, so let's use semi-topologies to explore notions of consensus. So let's consider a function from our semi-topological space P to some set of values X. And I'm going to call this function continuous at a point P when it's constant on some neighborhood. Now, being constant on a neighborhood means that the whole quorum of P, for some quorum, agrees on a value of F in X, right? So it's, you get the maths, but let's give an example. We might both look at a car on the street. We might look at a car on the street, and some people might see it as blue, and some people might see it as green. So imagine us in a group, and we might say, is that car blue or green? I can't tell. And we all sort of peer at it, and we're trying to decide on our function F. And then some people will say, ah, it's blue. And other people will say, nah, I think it's green. That's how I see it. So then we have a function from P to blue or green. And then maybe I am trying to decide, is this thing blue or green? So I look around for a set of people that I trust in this group. And if they all agree that it's green, then I might say, okay, fine. I agree it's green. Smile if that makes, react if that makes sense, and react negatively if it doesn't. You can see some smiles and nods. Good, thank you. And this is just a mathematical rendering of what I just said. If I can, here we are. This is just the equation for what I just said. There is an open neighborhood such that contains P, and F is constant on that neighborhood. Now, let's suppose that we're in the street and we're looking at this blue-green car, and everyone's saying that it's green, and I say, no, to me it's blue. So I'm not agreeing with any of my quorums. This is a discontinuity, and we could call me then, I'm Byzantine, because there is no quorum, there is no association to which I belong with which I agree. So let's formalize that. We can think of these functions here as observables, right? And some of you, I don't know, you might be familiar with the notion of an observable. So if we have a system, then typically we fix some collection of observables, and these are the things that we can measure about it. So we're going to fix a set of observable functions on our semi-topological space, And we'll say of P that if all the observable functions are continuous at P, then P is well behaved. And that means there's no observation on the world where P disagrees with all of its quorums. There's always one that it agrees with. And if there exists some observation on the world F such that P is discontinuous at F, so there is no neighborhood of P such that P agrees with that neighborhood, then we call Byzantine. Call P Byzantine. And note that P doesn't have to disagree all the time for every observable. That's not what this says. It just says that there exists an observable such that P is Byzantine for that particular F. And the analogy I give here is being scammed on the internet, right? So you go onto, I don't know if you have Gumtree in the US, but you go onto a sell and swap site, right? And you meet a really polite person who's offering you what you want at just the right price. And they're very polite and they're very responsive and they've got a web page. So you give them your money and then they vanish. The final observable fails. Blast, you've hit a Byzantine agent, right? But what made this agent so dangerous is that for most of the observables, they were absolutely fine. They did exactly what they were supposed to do. It's only on the last step that you discovered that you were doing business with the wrong person, right? I knew I shouldn't have sent all that money to that Nigerian prince, but how was I supposed to know? So that's being Byzantine. You don't always have to be uncooperative. You can be uncooperative when it suits you. But the fact is you could be uncooperative for some observable. So here's a concrete example. We take our friend, the real numbers, our first, because every topological space is also a semi-topological space, right? So that's fine. And our observables are functions that are continuous away from zero. And this is a step function. It observes whether x is less than or equal to 0. It returns 0 if so, and 1 otherwise. Then we have one Byzantine participant in our universe, which is 0. I haven't drawn a picture of this, but the step function looks like that. It's very familiar. That's fine. Another way to do this, which is relevant in the field, is to a priori fix. We fix a set of well-behaved participants. So a participant we kind of anoint them. We say, thou shalt be well-behaved. And then we do it the other way around. Instead of fixing the observables and deciding who's well-behaved, we fix who's well-behaved, and then we let observables be precisely those functions which are continuous on the well-behaved participants. And then you can prove a trivial lemma that your well-behaved agents in this previous sense are well-behaved precisely when they're in P by construction. I mention this because in the literature, this is how it's done. That is, well-behaved participants are typically assumed to be anointed, and the Byzantines are Byzantine because they're marked as Byzantine, and that's just what they are. So it's just a matter of perspective whether you fix observables and discover who's well-behaved, or fix who's well-behaved and then decide what your observables are. In summary, the problem of consensus, I put it to you, is the problem of computing an observable. That is, let's suppose you have some big complicated semi-topological system and you want to reach consensus in this universe. Computing a consensus is precisely, by these definitions, the problem of finding an observable. If you unpack all the layers of what I said, because an observable F is going to be, right, sorry, in this universe here, if we've decided who's well behaved, so our observables are precisely the continuous functions,
I can't hear you anymore, Jamie.
Can you hear me now?
Yes.
I'm sorry, my Zoom cut out. I don't know what happened. So as I was saying, we can identify the problem of consensus with now a concrete mathematical question. Can we construct, can we actually compute an observable? Any questions on this so far?
So if we take the other view, the question is, can we compute a continuous observable?
Yes, sorry, that's right. So by construction, observables are things that are continuous on well-behaved participants.
Right.
Yes, I'd agree with that, Huffman. A constant function is well, actually, no, sorry. I've confused matters. I apologize. So on the previous slide, I said we fix a set of observable f. So in this way of setting things up, a function is observable when we say it's observable. So Hoffman, I don't know your real name, I just know your handle. A constant function will be unobservable if we put it in capital F, right? But if we take this second example here, where our observables are precisely the things that are continuous on well-behaved participants, then indeed, yes, a constant function is by construction continuous on everything, and therefore will be an observable, but only if we start with well-behavedness and work backwards to the observables. Does that answer your question, Huffman? Thank you. Thank you. Okay, please, are there any more? Ask me another question. Yes, we are. We are going to talk later about what the input is to the consensus computation. Absolutely. Right now, I'm just describing the problem mathematically. In the last section of the talk, I'll talk about slices, and we'll get to that. More questions, please?
Well, maybe one question could be whether we can have observables that are not constant. Because if we're thinking of consensus, usually
there you are. That's an observable. That's an observable that's not constant. Right. Yeah. Thank you, Juliana. So any continuous, intuitively, you're probably going to want any function that's continuous away from your Byzantine participants to be an observable. That is, if someone knows who the well-behaved and Byzantine participants are, that's a cheap way to build observables, but you don't have to do it that way. You can just open up a bag of observables, scatter it on the table, and that will then tell you what the well-behaved participants should be. Thank you. Does that answer your question, Juliana? I think you nodded. You're yes. A very, very small icon. Thank you. Perfect. Okay. So let's just talk about a few more things that turn up in the literature. Let's consider observable functions from R to R that are continuous away from this set here. And this is, as you can see, a sequence of real numbers, in fact, rationals, that is tending towards 0. So 0 is a limit point of Byzantine participants. So a function it has to be continuous in between these points, but on this point it can step, it can jump, it can do whatever it wants. So it's impossible that the notion of well-behaved doesn't even make sense for 0 because it's surrounded by crazies, right? No matter what neighborhood, no matter how close you get to 0, there's an infinite number of crazy agents really close to you. In the stellar literature, this is called befouled, and this set is called a blocking set for 0. It's a set that makes it impossible for 0 to have any sensible notion of good behavior. Topologically, this is a familiar notion, right? And just to be clear, this is a new observation. You won't find this in the stellar literature. We are noting, if we look at it topologically, befouled and blocking sets are just limit points. A limit point is a set that intersects with every neighborhood of a point. That's it. So blocking sets are just convergent sequences. I forgot to put that in the slide. This is a convergent sequence and its limit point is 0, and that's it. So we can say that the notion of blocking set identifies with the notion of a limit point and a convergent sequence, which is really nice. Any questions? So befouled is Ryan Scott has asked what exactly makes it befouled. So befouled is a definition, and it's easier to see this topologically. So Ryan, imagine that, imagine there's a trail of ants crawling towards you, forgive me, and they get closer and closer as they get near you. So no matter how small a step you take, you're going to step on an ant, right? That's a limit point. So there's lots of points here, and they get closer and closer and closer to 0. And no matter what epsilon you give me, like you say, okay, I'm going to give you a trillionth, but there's an infinite number of rationals in the sequence less than 1 over a trillion. So you can't escape this sequence of points. Ryan, does that answer your question?
Maybe I can make a comment related to stellar.
Please.
So yeah, so in the stellar system, when we're trying to reach consensus, there are participants they have good intentions, they want to be well behaved, but every one of their quorums has a malicious participant in it. And therefore they cannot possibly reach consensus with the others, because they can always be tricked by the malicious guys. And that's why we call them befouled, which is the same notion here.
Thank you. So the way I think of this is that you're coming home and there's ants everywhere. So you go into the house, you'll be safe there. But no, there's an ant in the house. So you go into your bedroom and you shut the door. So you're going to a smaller and smaller neighborhood, seeking safety in smaller and smaller quorums. But there's ants still. So you jump into the bed and you pull the covers over your head, and there's an ant on your pillow wiggling its antennae at you. So no matter how small your neighborhood, there's going to be one of these malicious participants. That's the notion of befouled, and it's topologically precisely the notion of a limit point. Thank you. Any further questions? Okay, can I carry on? Somebody type yes, just to reassure me, please. Thank you very much. Now, there's something else that malicious actors can do. Up till now, I have assumed at least that f does return a value. But here's an example of a function that does not return a value. F isn't just discontinuous at 0, like the step function, it's actually undefined. In fact, if you draw a graph of this is a classic graph, okay? It goes to negative infinity below 0 and comes down from positive infinity. So this is a classic function that's really quite bad at 0. And that's okay. We can either generalize a little bit, so our observables are partial, so they don't have to return values, or we can just add to P a bottom or undefined value. This is, many of you will have seen this in computing, right? A non-termination value. And then we just say that participant is well behaved when every observable is defined and continuous at that participant. That's fine. So interrupt me if you have any questions on that, but I would hope that with this audience, this will be clear. So my point is, over the past few slides, I've tried to convince you that I have argued that semi-topologies are a useful language. With Giuliano's guidance, we've read through some of the consensus literature, and we've always been able to find a compelling topological and quite precise analogy in semi-topologies. If you look at this and you think, oh yes, I recognize this phenomenon in topology, then please be in touch. We would love to hear from you. Thank you. So I will move on. As always, stop me if you have a question. See where we are. Let's talk about consensus clusters. So we take a semi-topological space, and I am going to say that, and this is just notation, right? X entails Y when they intersect. That's it, just a definition. This is obviously taken from logic, and that's because we're going to see a behavior that resembles cut in a minute. But notice this is a very simple logical judgment. It's a logic of if and only ifs. X intersects Y, if and only if Y intersects X. And I'm going to call a set of participants a consensus cluster when, if P intersects C and C intersects P primed, so if P and P primed both intersect C, then P has to intersect P primed. But instead of intersect, I'll say entails. So if P entails C and C entails P primed, then P entails P primed. A reformulation of this is that C is a consensus cluster when, for any 2 points in it and any 2 neighborhoods, right? So this C and this C prime, they are witnesses to these intersections. These 2 neighborhoods must themselves intersect. I have not seen this condition in the topology literature. It's a form of strong converse to the Hausdorff property. And this is where the consensus literature has contributed a new idea, as far as I know, a novel idea in topology. I should also say, if you read the papers, thank you. This definition does not assume that C is open, but we will mostly be interested in cases where C is open. If we assume C is open, we can prove a further property, which I'll come to on the next slide. Thank you for the question. The question was, does C have to be open? The short answer is no, but if it is, then good things happen. I will also point out that you won't see this written like this in the stellar literature. This has come from the semi-topological rephrasing. The definition in the paper looks quite different, but that's what it means. Now let's prove a lemma. If we have some function, right, and we have a consensus cluster C, then if F is continuous on C, then it has to be constant. And that's why we call it a consensus cluster, because if we've built one of our observables, then everything in C has to agree on the value of the observable. I'll just mention this depends on X being a discrete topological space, but that's fine because for simplicity, that's all we're talking about. If X has its own semi-topological structure, then this lemma would need to be generalized. So this is actually a special case of a more general lemma, but that's fine. That's very good. And the proof is kind of trivial. Because F is continuous, there have to be quorums, P and P primed of C and C primed. And because these quorums intersect, F of C has to be equal to F of C primed. Remember I said that F is continuous when for every point C, there's some constant quorum, some quorum of C such that F is constant on that. Right, so I'll rephrase that. We pull these 2 quorums such that F is constant on them to open neighborhoods of C and C primed. And because these open neighborhoods must intersect, the values of F at C and C primed must be equal. Questions, please. Okay, is this clear? Can I move to the next slide, please? Perfect, thank you. I'll take that as license to continue. Whoops. .14, so I'm 3/4 of the way through. Okay, now here's the nice property I promised. Let's suppose that we have 2 consensus clusters, C and C primed, and they intersect. Then I claim that their union is also a consensus cluster. So the union of intersecting consensus clusters is a consensus cluster. The proof, when phrased in this language, is dead easy, right? Because let's suppose P intersects with P, suppose P entails C, And because they intersect, C entails C primed, and also C primed entails P primed, then obviously P has to entail P primed. Simple. So that concludes the proof. I just want to mention another way of looking at this. Instead of thinking of it as entailment, you can think of it as path connectedness. And to be clear, I'm not saying that consensus clusters are path connected. It's an analogy, but it's a good one. And then we say, if there is a path from P to C, and a path from C to C primed, and a path from C primed to P primed, then there's a path from P to P primed. Simple. And this is one of the main lemmas in Juliana's paper, rephrased in semi-topological terms. It's an important result. There's a corollary which you can prove, that an ascending chain of open cut sets is also an open cut set and a consensus cluster, that is. And this tells us that this is where the stability is going to come from. A semi-topological space will partition itself naturally into disjoint maximal cuts, that is, disjoint maximal consensus clusters, along with some lonely points that are not in any consensus cluster. And this is exactly what we do see in real life, right? You've got in Glasgow, some parts of Glasgow, you've got the people who wear their tracksuit bottoms rolled up at the ankles and the people who wear their tracksuit bottoms tucked into their socks. And if two people from these two different consensus clusters meet, they're going to fight. It's considered obligatory social behavior, right? So this is a group that have organized themselves spontaneously into two disjoint maximum consensus clusters. One might call them tribes, and these two tribes are very sticky, right? People belong to them. So this is a mathematical version of that observation. It's just come out of the math. I think that's so cool. And this also goes some way to explaining stellar stability, because mathematically the system wants to form these partitions. And in a connected world, you've got pretty good chances that there's only actually going to be one consensus cluster. And that's what we want, right? A consensus algorithm wants everyone to agree. If people disagree, if you have multiple consensus clusters, then the consensus algorithm has failed, or consensus system has, or at least is less useful. So this is a good thing. This is desirable behavior. Can I carry on? Type something if I can continue. Okay, is there a question? Okay, thank you. Now, this is from the paper, the quorum sharing property. I'll tell you what it means to me. It means that an open set is a neighborhood, a quorum for every point that it contains. This is the definition of an open set. And in the paper, property 1, you can see from the numbering, this is an important key property of stellar, and it identifies precisely with the notion of open set in topology. Therefore, we can say that quorum is equal to open set. That's what it is. I will continue. So a little bit of justification. So semigroups are groups without inverses. But semigroup theory is a rich field in its own right. It has its own character. So it's quite common in maths to see pairs of definitions that differ in just like one apparently innocuous axiom, but that gives the field a very different character. Semigroup theorists, and being a, broadly speaking rule of thumb, semigroup theorists don't have any group theorist friends and vice versa. They are distinct fields. And semi-lattices are closer to lattices, but still it is a different field. And it's quite instructive to look at, if you like, the median model, the typical, the average topology and the average semi-topology. So the average, I say average in the sense of median here, that is the most common, the thing that is in the center is R, the real numbers. If like me, you studied maths in uni, then the first topological space you were taught was this thing here. That was it. This fella is the canonical topological space. There are lots of others, but this one is ours. And the median function of interest is our continuous maps from R to R. Right? In topology, broadly speaking, we're interested in scenarios with infinitely many points and continuous functions and separation axioms. So I went on the Wikipedia page. There are 18 different flavors of saying when a topological space is separated. So there's Hausdorff is the most common one. So in summary, topological spaces are big places with lots of points that are far apart. In semi-topology, at least for this application, almost all of this is reversed, even though the definitions are epsilon away from one another. We're interested in finite universes because we're modeling consensus. The world might be large, but it's still finite. And we really want our spaces to be non-separated. The notion of a consensus cluster has to do with points being really close to one another. And yes, functions are continuous, but it's key that there might be Byzantine participants, that is, discontinuities of these functions. If we think about the function x goes to 1 divided by x, the fact that it's discontinuous at 0 is kind of embarrassing, and the lecturer is going to kind of hum and ah and say, well, yeah, but it's continuous most of the time. But in consensus, the discontinuity is the point. That's what we're fighting. That's what we care about. We want the system to be robust in the presence of discontinuities. So that's what the story is all about. Yeah, so we can see there's a field, there's a mathematical field trying to come out of this, and we can see the outlines of it here. I will move on. So here's a summary. This is what comes from the stellar literature. This is its rendering in a semi-topological language. And there's one more thing that I really want to tell you about, which is slices. Giuliano, can I tell them about slices?
Yes, of course. You still have a little 8 minutes, I think.
Okay, well, 8 minutes to talk about slices. So this all has to do with computing open sets. Remember, an open set is a quorum, right? So supposing we have some set of points and we want to compute an open neighborhood of it. And in practice, the example is there's like a participant, let's take me as an example, and I might have a set of people that I trust, and they're in the system, and now I want to join the system. But in order to join the system, we need to compute what my quorums are. But the problem is, quorums have to be neighborhoods of every point within them. So it's not just about me, it's not just about who I trust, it's about who the people that I trust, and the people that they trust, and so on. So for example, I trust my wife, but I won't tell her my credit card PIN, because that would be bad practice, right? Even though I trust her, I don't know, maybe her sister would walk into her office and see it written down on a post-it note somewhere. So I just don't go there, right? So that's what open sets are. They have this transitivity property. And that makes them quite expensive to actually compute. So to be clear, mathematically, open sets are vital. They're all over the literature. But actually computing one is quite hard. So we need more efficient ways of algorithmically working with these things, hopefully that avoid computing too many open sets. And Stella has a way of doing this. It introduces a notion of slice. So let's just take a look at this. In my first picture, this is an open set, and I'm going to call this a slice, and this is going to be a closed neighborhood of the point. And closed neighborhoods don't have to be neighborhoods of every point within them. They can have a boundary. So that's like me and my wife, right? I trust my wife, but there are other neighborhoods, like my wife might have other neighborhoods that she trusts that maybe I don't necessarily trust, But so that's, from my point of view, that's a neighborhood. So in Stella, a point doesn't nominate opens. That's computationally, that's a bad idea. What it actually nominates is slices. And I would argue that slices correspond to closed sets because they can have a boundary. And if we know closed neighborhoods of every point, we can compute the opens just by, for every point, we add some slice, and now we have a larger set. So for every point, if there isn't an open neighborhood, if there isn't a slice in there already, then we add another slice and so on. And pictorially, that's equivalent to going to this boundary here and adding some closed sets of points on the boundary and iterating indefinitely, infinitely if necessary, until we get to this big open set. I hope pictorially that makes sense. Any questions on that before I move on? Okay, say something if I can move on, please. I need a reaction. No, so the Atchke has asked, can sets be open only in one direction? So let me finesse this. We can construct our semi-topological space. When we do so, we just need to provide open sets. So for example, we could take the natural numbers and a set is open when it's closed to the right. So greater than or equal to 0, greater than or equal to 2. That's a perfectly valid semi-topology. In fact, it's a topology.
I was wondering in R2, right? So we're talking about open and closed sets, but if you could have a set that's kind of closed on two sides, but open,
yes,
open up and down, and then right?
Yeah,
so,
sure.
So how does that fit with the consensus, or does that not make sense in this context?
Well, you haven't told me what your, thank you for the great question. You need to tell me what your open sets are.
I was thinking R2 with the normal topology.
Okay, so that is neither open nor closed.
Exactly.
It's neither completely open. It would still make a perfectly valid slice.
Okay.
So I need to be a bit more precise here. The notion of slice corresponds to the notion of closed neighborhood. What's happening in R2 though is that in topologies, I actually have this on a slide, in topologies, the closed sets are the complements of the open sets. So your point here is there are sets that are neither open nor the complement of an open. But in semi-topologies, that breaks down, and that's okay, that's fine. So it's not the case that the complement of a slice is a quorum. Does that make sense?
Yeah, okay, thanks.
So what we could do, we could build a perfectly valid semi-topology where we take open sets as before from the topological structure, but we just declare closed sets to be ones that are either closed in the normal sense or at least closed in a particular direction. And that would be a completely valid semi-topology on R2. Make sense?
Thanks. Yeah.
Great question, thank you. So yeah, so implicit in this is an idea that for semi-topologies, if we want to take account of slices, we'd need a set of opens and a set of closed. And that's what Stella does. It has quorums and slices. So in short, this is the conversation we've just had essentially. In short, I propose to identify slices with closed neighborhoods. And this is really fruitful because there are various notions of continuity, like the inverse image of an open should be open, but there are other notions of well-behavedness, like the pointwise image of a closed should be closed, stuff like that. So it's really interesting to think in a semi-topological view, what are the well-behavedness conditions that we want on our functions? And there need not be one right answer here. Okay, so to sum up, with 1 minute to spare, I regret I can't offer you any immediate algorithmic implication, but what I can propose is that this topological language is really powerful and it's compelling. maybe this will, I hope it will be helpful, for example, to Stella, to explain what's going on in a language that will be familiar and compelling and diagrammatic to a large community of mathematicians. It also, at least for me, makes the statements and proofs of properties of algorithms much easier to understand. To the extent that I understand Giuliano's work, I understood it by translating it into semi-topologies first. And I would argue that some proofs which might have seemed long and arbitrary become short and natural when using this language. And I tried to demonstrate that with a lemma about consensus clusters. And it might make the system easier to motivate. That said, here's one path which I'm not qualified to pursue on my own, but there is, I know, a large literature on graph connectivity. And it seems to me that what's going on here is there's a notion of semi-topology, but there's also a notion of combinatorics and connectivity. Thank you for watching. So in particular, there's a whole field that studies how, if you just randomly choose a graph, when is it fully connected? So there might be people out there who'd be really interested in this now that it's been observed that there's a connection to topology. And the reason I'm here in this talk, the point of the talk for me is applications and ideas. You're out there, you've got your own ideas. If there's something that sparked an idea here with you, then let us know, because we need more, right? To turn this into a paper, I feel we need some extra stuff. And I'm hoping maybe that you or a friend of yours or someone in your quorum might be able to help with that. Thank you very much. Over to you, Giuliano.
Thank you very much, Jamie. This is very interesting stuff. I think, yeah, we're out of time, but probably some people have more questions. If Jamie, you still have a little time.
Yeah, I'm cool. Fire away.
Yeah, I don't have a question on the technical side, Jamie, but it does seem to me that it would make sense to try and turn this into a form where you could talk to the Stella people about this, because it sort of seems like, I mean, explanation is great, but it seems like maybe one of the places this could be useful is exploring the space of possible algorithms. So, you know, maybe there are places where, because we don't understand the shape of the problem using the previous theoretical setup, you could understand it better using this. I don't know Stella well enough to say whether or not that's the case, but it seems like at least plausible that that could be so.
I agree. Yes. Mm-hmm.
Have you had a chance to? I know Giuliano, you have connections with the Stella people. Have you talked to them about this this yet?
Briefly, but I didn't get much feedback so far. I know that that's something that could be very interesting in practice. As this connectivity aspect, because, for example, in practice, it's important to be able to compute what is your consensus cluster, for example, or which part of the system are going to stay coherent or not. And this is not well understood how to do this.
Yeah, it's very interesting work. So thanks very much for presenting it.
Thank you, Mike. Thank you. The obvious mathematical question to ask is, what are the functions between these things? Right. And as I said, there's multiple potential notions of continuity, because opens and close are now more loosely connected. So there's different kinds of structure you could think about preserving, and there are Byzantine participants as well.
This is completely off piece, but I remember, was it like Heidi something or other who had a paper recently about kind of unified theory of consensus algorithms? They wrote their PhD thesis. Giuliano, did you see this work? They were out of Cambridge. In fact, you know, Jamie, you might know them. I don't remember whose student they were, but they were. I wonder if, you know, it sort of seems like what you're reaching for is some kind of unifying theory here, and I wonder if that would be interesting to look into.
What's the name, please?
I'm completely blanking on it, I'm afraid. It was, it's Heidi something, I think.
Yeah, I'm
One
not
second.
sure.
Heidi Howard.
That's it, Heidi Howard, yeah.
Excellent.
Yeah, I don't know if you know
Got a
her work.
PhD. No, I don't know Heidi. I now know she exists. Thank you for that.
So if I only know this at the level of reading the abstracts of her papers, but if I remember right, basically what she came up with is sort of unifying characterization of some different categories of consensus algorithms, and proved some interesting theorems about it. So it might be interesting to go and take a look at that and see whether or
Mike,
not
thank you so much. That's fabulous. There's a paper here. This title contains "Have we reached consensus on distributed consensus?" which is exactly what you're talking about. Perfect. Thank you, Mike.
Yeah, and I think she won like the sort of BCS Best Thesis Award or something like that. So, you know, her work is very well regarded.
Excellent.
And out of Cambridge as well, I think. So I don't remember who she worked with, but someone from Cambridge.
Mm-hmm. Mm-hmm. I'll look it up. This is exactly what I was hoping for. So I'm going to state the obvious, right? There's 30 people in this talk. If this sparks ideas, let me know now. Let us know now or later. This is really important. Okay, so I'll look up Heidi. Thank you, Mike. Any other ideas?
I got to hop off, but thank you very much.
Oh, okay, that's an idea. Thank you, Mike.
Yeah. Jamie, I'm going to go
Thank you
ahead
for,
and
yes.
stop the recording right now, but everybody
Yeah.
stay on who needs to. I mean, I know many people have dropped off. I think we're down to about a dozen now. So
Yeah, stop recording. That's good.